Hi, Miss Anamika.
Hello, Matilda. Yeah, I'm just waiting for you. Yeah, let's wait for students then.
Yeah, sure.
Yeah, thanks for joining.
Should we wait for some more time or what should we do?
I think you should start, Matilda. Let Nitin, can you start the streaming, please?
Yes, sure, Anamika, I'll do that.
Okay. Nishant, you can start, I guess.
Yeah, okay. Yes. So basically, in the assignments and all, what we did is the speaker diarization part. So there, it has been shown that this for speaker diarization, we were using ECAPA TDN model to generate this the speaker embeddings. whatever speaker embeddings are there that were produced from eCAPA TDNN model. So in this session, what we will do is that we will discuss eCAPA TDNN model in detail, like a paper is there on that. So we will discuss that, and after that, in speech brain, we will try to understand how we have to implement, like the model has been there, how you have to train, how we can get the speaker vector from TDNN model. So in your assignments only, you have just imported that speech brain model. From that you just took this speaker vector embeddings. So how this speaker vector embedding you got, and what network they used in eCAPA TDN, that in the paper itself we can discuss it. So now I'll start presenting this paper, and I'll discuss the basic architecture and everything, the whatever data set and what they have used. So we'll discuss for that. I'll start presenting the paper once. Yeah. So this is eCAPA TDNN. So this eCAPA stands for Emphasized Channel Attention Propagation and Aggregation in TDNN based speaker verification. Actually, TDNN means time delayed neural network. So basically, previously what they used to do, they used time delayed neural network for speaker verification, and some ASR task also they used to use this method. So what in eCAPA TDNN what they did is they added some of the networks, like emphasized channel attention. They used propagation via residual connection, so that it will be discussed in the architecture itself. So here is the architecture, what the model they are using. So for any uh, speaker verification task, here they have used MEL spectrogram, MFCC vector. So for a speech audio, we calculate this MFCC vector for in here they have said that they use 3 seconds of audio, and they calculate, they have taken 25 second frame size, and 10 second will be the hop length, like whatever they'll shift the frame by 10 seconds. So for every frame of 25 seconds, there will be a MFCC 80 cross 1 MFCC vector. So over the whole time step, suppose T will be the time step. So 80 cross T will be your input feature to this network. Now, what TDNN does is, it's basically a convolutional network. So TDNN networks are convolutional network where they uses. So in this, what they have used is one thing is that this emphasized channel attention, like they have used this by adding this channel, they can better focus on speaker relevant parts of audio. In TDNN, you will not get, means the accuracy was good, the better performance was good, but in eCAPA TDNN, they try to extract the speaker information or on a broader area, like, and after that they use some residual network. You can see this residuals networks are there. So the with the help of these residual network, you can get temporal dependencies and global dependencies also, and the vanishing gradient problem can also be reduced with this thing. And this is the SC, like SC residual to block they have given. So this is the SE2 residual block, where this I'll explain you in detail after some time. Okay, then now if we come to architecture, so we have talked about embedding, input embedding layer. Then comes TDNN block with squeeze and excitation layers, the SC residual block. So in this, what they are doing, suppose you have a input 80 cross T input vector from first convolutional layer. If you have C channels, so the output will be C cross time steps. So each time step now will have a C dimensional vector. Suppose C will be 20, 30, whatever you take. It's a relatively a hyperparameter you can take. So this C vector is then fed to here the input of con1d, and after that in what here they are doing mostly in SC block is that squeeze operation is going on. Like suppose you have a C channel vector. What they are doing in time step, suppose C cross for every time step for 1 second, 2 second, 3 second, 4, it's not will be in seconds, but I'm just for explaining purpose I am telling you. For 1 second, 2 second, 3 second, there will be a C vector will be there. C cross one vector for 1 second and C cross this for whole time step. So what they will do is they will take a average value of the whole block, like that they have told in the paper that will be their descriptor vector Z. Here only they have shown somewhere they have told. So this descriptor vector they have told for SC block, whatever they'll average across the time steps. So you will get one descriptor vector. For this descriptor vector, using this descriptor vector, the excitation step we can calculate, like the weights for each channel. So what they are doing is for each and every this X descriptor vector, whatever they'll get, they'll try to find the weights which vector is related, means how much weight is there, because in speaker verification task, what's happening is you have to find relation between each and every time step side, like how the embeddings are related to each other in for one speaker, for a single speaker. So here now you for t time steps you have t vectors. So in each vector how much they are interrelated, they are trying to find it. So after that this discriminator vector z for so they try to learn the weights for each and every z vector. With that weights excitation operation has been done. So in this excitation operation the weight had been you can learn the weight. They'll take it to a lower dimension vector and they learn the weight according to it, and after that channel scaling will be done. So here you will learn the weights of each and every vector, that how much, suppose I'm taking I'm saying a name. So a and M has a suppose A has a different vector specification and A is related to M in a different way. So they have interrelation between them. So weights for A and L will be more. A and N means what I'm trying to say is that the weight will be decided according to the speaker vector, how you can differentiate, discriminate between them. So this will be done. So whatever weights you will get, you will just multiply the weights with the given z vector, and then the output will be there. And after that this all this dilated these vector are dilated, like here you can see, like dilated convolution are used, like d is equal to 2 means two order dilation has been used, like between two samples you will put two zeros, and like that you will take convolution between them. Here three dilation has been used, and here four. These dilation what means is, like you are trying to capture global dependencies, because CNN, if you take a kernel size of 3 or 4, it will capture the local dependencies very properly. But if you take dilation 2, 3, 4, so it will try to capture larger dependencies in this. So this and these residual connection are also done so that the global dependencies won't be missed. So with this, suppose C cross T will come here and C cross T will come here and C cross T. So they will concatenate all these 3 C cross T, and after that they will once more take a con 1D. So this is a hyper parameter only. 1536 cross T vector has been produced. After that, attentive stat pooling need to be done. So this is a attentive stat pooling is something they are trying to summarize this frame into fixed size embedding, because your audio will be of suppose your audio will be of 3 second and you have a for 4 second a different number of frame will be there. What they are trying to do is to create a fixed number of vector. Like if you want to match the speaker embedding with this, so you need a fixed vector. It's to match. Like if the speaker embedding what we have is of 3 seconds. Suppose a audio means in speaker verification task, while in our phone we have this we can open our phone by saying few words. So if it's of 2 seconds, so and your model has been trained with a 5 seconds, so it will not match. So for matching purpose only, we just take a vector 192. They have taken 192 speaker embedding vector. So what basically they are doing, they are trying to do is this attention pooling is trying to do is to produce a constant like a fixed vector that can be compared with the speaker embedding that we will say. So this attention statistical pooling is doing this only, and they are calculating by weighted mean and weighted standard deviation calculation. So weighted mean calculation, in this pooling only, suppose you have 1536 comma t, dimension vector is there. Here 156 comma t time step dimension is there. Now you pool it to a single dimension, like a single matrix will be there of 3072 cross 1. So, and this matrix, this will be taken to a lower dimension from this fully connected, and fully connected this batch normalization has been done. And after that, this embedding what you are getting is 192 cross 1 embedding. This is the speaker embedding what you get, and in the assignment what you have used is this speaker embedding of e kappa TDNN. And after that, if you they have in this they have used angular margin loss. They have used, it is a type of loss. I'll explain 1 second. Yeah, this is type of loss, angular margin loss. So what angular mass is, suppose for classification task we use this type of loss. Like cross entropy can also be used, but uh, we don't use cross entropy in this type of thing. What suppose you, this is your first class, so it lies at an angle theta 1 with the class 2. In between them they have an angle theta 1. So this softmax, what you do, this probability of getting of this is normal softmax, and this will be the softmax what we are using, angular softmax. So angular softmax is another thing, but here they have used is this one, fixed decision margin. What they did is they took a threshold of margin, like delta theta or something, they for to decide the boundary which will the speaker embed, whatever speaker embeddings will be there, like S1 and S2 be the embeddings of two speaker. So they'll provide a threshold of the decision boundary that will clearly that will be also be learnable, means that it will learn and define it, that what decision boundary should we do for better, means what you call we can say between both the classes we can get a better clear view that they are different class, they come from different class. So this type of loss function they are using. And on the data set what you are using in the experiment also, you have used Voxelab data set. So here also in kappa TDNN they have used the same Voxelab data set. And what else, and this evaluation matrix also they have used, but means after that they have used this AM softmax and they have used, but here you don't have to use this such type of evaluation matrix. Like you just need to have a this 192 cross 1 vector and give it to your this task, dialarization task. Like this 192 cross 1 vector will be used in your dialarization assignments. Matilda,
Yeah. Thanks, Nishant.
so yeah, you can
Yeah.
explain.
So what I'll do now is like this model actually it was trained with some toolkit called yes, Miss Anamika.
Yeah. Matilda, just I thought maybe yeah, we'll cover what you are going to cover.
Yeah.
But before that, because students are here, right? So if
Mhm.
they have any questions, maybe it'll be good to take those questions and then we can
Yeah,
continue with
sure.
what. Yeah.
Any questions until now?
Yeah, Govind seems to have a question. Please go
Govind,
ahead.
yes, Mr. Govind.
Yeah, hi. Thanks for the session. I have basically two questions. The first
Yeah.
question is, uh, see, in week 5, we did the language detection, right?
Correct.
And here we are doing speaker identification.
Correct.
Can you give me some intuition
Yeah.
behind how these these are fundamentally different? Like in the week 5,
Mm.
whatever the data set that we have,
Mm.
so we have there also for each sample there
Mm.
was an array, right? There was an array of of float values,
Yeah.
and that one we took it as a a source, and
Correct.
we did some processing and we came up with some embeddings, etc. Right?
Correct.
And here we are dealing with mel values, as I understood, right?
Actually, it is HEFBank, MEL filter bank features. Okay, not MFCC.
Okay.
Yeah.
So how are we able to achieve what we are able to achieve with these vectors? Like, how are we able to? Can you give some background on how are we able to achieve? Because in vision models, it is
Mm.
understood in the sense like we are doing on a two-dimensional image. We are doing convolution, and
Correct.
we kind of have an intuition that between the pixels there are certain features that can be extracted by convolution operation itself,
Correct.
by identifying the edges and
Mm.
the changes in the contours, etc., right?
Mm.
Similar to that, can you please give us some intuition about week 5 and week 6, whatever we are doing, how are we able to achieve it? How, what is the intuition behind these two tasks, and how are
Mm.
we able to achieve what we intended to achieve?
Okay.
That was the first question. After that, I'll come to the second question.
Okay. Fine. So, so this features, right? Okay. In your first assignment, you took wave to wake features. Am I right?
Yes, yes.
Correct. So you took wave to wave features, and from the wave to wave features, what did you do? You came up with some embedding, and then you fed it to some classification model, which was based on convolutions. Correct.
Yes.
So this wave to wake, actually, this wave to wake was trained only on LibreSpeech data, whatever model we had given you, which is pure English data. Okay.
Okay, but see, for
Yeah, I'll
where
come
I'm
to.
coming from is the source is both for both of them. The source is audio clip, right?
Correct.
So how are we able to come to a stage
Hmm?
where we are able to do different tasks? Basically, that was the question.
Uh, okay. So first of all, it starts with the features. Okay, whatever it starts with the features. So in your first language ID problem, what you started with was some features from wave to wake. Wave to wake actually is a model that is trained on some kind of infilling kind of task. Okay. So if it is infilling kind of task, what happens is it tries to understand the language. Am I right?
Yeah, please go ahead. I'm trying to understand.
Yeah,
Please go ahead.
okay. So it is trying to do some kind of infilling, which is actually trying to understand the language. But for the purpose of your experiment and stuff, we did not give you some multilingual wave to wake. What we gave you was a simple LibreSpeech trained wave to wake, and you were given a task where you should be like getting the features for three languages, if I'm not wrong: English, Romanian, and Spanish, right?
Yeah, that's correct.
Okay. So this was just a see, the experiments that we have set up for you might not be like completely realistic, because this LibriSpeech model might not give good features for all the languages. Okay. If it is a multilingual model which is trained on all the languages on which you wish to perform your language identification, then it would do a better job. That's why if you take a completely different language and extract features from the model that we have given you, and then you try to perform some classification, it will not perform good. Okay. So basically the language classification actually stems from the language understanding part of your Wave2Vec. Ideally, you should have had a multilingual Wave2Vec model to extract your features if it has to like do a better performance for many languages and stuff. Yeah, Jaydev, you have a doubt?
So what is the difference between the free speech model and the Facebook base 960 hours model?
What is free speech?
So the LibriSpeech, sorry.
LibriSpeech is a data set. Okay, it is a
Oh, I
data
see.
set.
Okay.
Yeah, it is a 960R data set. It's a standard data set that is usually used to train all these, your pre-trained models,
And
self-supervised
it's only
models.
English, is it?
Yeah, it is pure English. And there is another set which is also multilingual. People are coming up with different things. Okay, but the 960R is a pure English model.
So
English
how is it
data
able
set.
to
It's
figure
a
out
data set.
language differences? I mean, this kind of underpins Govin's question.
Yeah. So, ideally, if we had given you a multilingual Wave2Vec, then that would answer your question. What we actually wanted you to do was to understand the steps basically. Okay. If you had used a multilingual Wave2Vec and maybe say that multilingual Wave2Vec was trained on some 100 languages, let's say, then that would do really well when it is a 100 language identification problem, because the Wave2Vec is trained like BERT. It's doing some kind of masked prediction, which is like an infilling task. Okay, so if it has to predict some masked portions of an audio clip, then obviously it has to understand the language. Correct. So if it
Okay,
is,
got it. So
yeah,
the experiment that we are doing is deliberately sort of, it has
yeah,
an upper
it's
limit
kind of,
to what
yeah,
it
yeah,
can do.
yeah,
Okay.
yeah, yeah. But the logic is you can use Wave2Vec features for language identification if it was trained on a proper multilingual
Multilingual data
data.
set. Yeah.
Yeah, that's right. Does this answer your question, Mr. Govind, about the language identification?
Yeah. I
Okay.
think if you can compare it with the second task, that will
Yeah,
be
for the
more
second
clear.
task, let me come to the second task. Second task, your doubt is how is it able to identify the speakers, right? With all these
Yeah.
features, the features that MEL filter bank features that we are feeding, correct? For you in images, it is pixels, correct? But here we are using MEL filter bank features. These MEL filter bank features are nothing but you take your spectrogram. You understand the spectrogram, right? You take the 25 millisecond audio windows. Okay, if say you have a audio waveform of 10 seconds, let's say, then what you would be doing is you will try to take a window of 25 milliseconds. Why that window of 25 milliseconds? It's because we assume speech is quasi stationary. Okay, it's not stationary, but it's quasi stationary in that 25 millisecond window. Okay, so we assume that the speech characteristics or that characteristics in that window are not going to change much. That's why people have come up with 25 millisecond. And when you take a spectrogram for 25 millisecond, it's also called as short time Fourier transform. Okay, so what you do is take a 25 millisecond window, get the Fourier transform of it, and then shift it by 10 milliseconds. Then you take another window, it's like overlap windows now. Okay, and then again get some spectrogram. Okay, so this spectrograms you have now. So for 10 seconds, let's say you have some I would just say x number of spectrograms with you. Okay, fine. So
Yeah. Yeah.
for this x number of spectrograms, what you would do is you would apply something called a MEL filter bank. What is a MEL filter bank? MEL filter bank is nothing but some triangular shaped filters. Okay, and how they are spaced is at the low frequency regions you put many maybe I can even show you a figure. Give me a minute. MEL filter banks. MEL filter banks. not. Just 1 minute. Mm, I'll share this video. Is this one visible to you people?
Yes,
Zoom
yes.
zoom it a bit. Okay. So this one, no, this thing is, it's basically triangular filters. Okay, you can see some triangles sitting here, correct? So some kind of triangle filters, and these filters are spaced such that at the low frequencies you have many filters. Okay, it's compressed here, so it's not so visible. So you have many filters in the low frequencies, and in the higher frequencies they are like very less filters, and they are also broader. The reason being that's it's basically modeled on how our hearing, right, the ear, human ear, how it works. We are more sensitive to changes in the low frequencies, and we are less sensitive to changes in the higher frequencies. That's why they have so many different filters, you know, some kind of, they are crammed into that low frequency region, because we have to figure out the changes, small changes in the lower frequencies. But in the higher frequencies we are not so bothered, because we are not that sensitive to the changes. So they want a system which can model how the human hearing works. Okay, so they came up with this filter bank thing. So you apply this filter bank on your Fourier transform kind of thing, whatever you have got, and based on the number of filter banks that you have chosen, you will end up with those many numbers. It's basically the energy in that particular in that filter. So that is the number that you end up with. So these numbers are basically the basis for your features that you are actually feeding to the model. So that it's equivalent to what your pixels are. Here you have the filter bank energies, and some log operations and stuffs happen, but we will not get into so much details of it. Anything more you want to know about the features? So these features,
Yeah.
because they have the discriminative ability, your neural network is able to process it, and then you are able to achieve what you are actually achieving.
So in case of the second task, whatever the MEL values that we are extracting, we are getting,
Correct.
they have a implicit order to them, right? We cannot actually
Yeah.
actually reorder them, right? We have to have them.
No.
We have to use them in a specific order. Okay,
Correct.
right? Now this is similar to the a picture where we have certain pixels and they are arranged in certain order to realize a picture, right?
Correct.
So applying a convolutional model on, I mean,
Hmm.
1D convolution on this makes little sense to me. But how does it make sense in the task one? Do we also have some kind of implicit order in the feature vector that we kind of get and we convolve over it? I mean, the con 1D.
Obviously. Yeah.
What is
Yes.
that?
For
What is
language,
that
what is
intuition?
it you are saying?
No, yeah, for the first task, yeah, for the language identification.
For the language identification,
Hmm.
so you have actually taken wave-to-wave features, correct? Wave-to-wave features, and you are saying, yeah, it is similar to that only. Na? Like how you cannot reorder your MEL filter bank features, you cannot reorder your wave-to-wave features also, right?
No, I don't know. I'm just
You
asking.
cannot.
What
You
is
cannot.
the
You
what
cannot
is the
reorder.
implicit order? What does that convey? What
So
does that
what you
order
get out
convey?
of what I mean, it is some kind of features, like how the model has understood about a language.
Is it at
Okay,
least temporal or not?
it has to be temporal, yeah.
Okay.
So
So the
what is
wave
the
to
doubt?
no, the wave to the feature vector that we kind of get over which we apply con 1D convolution
Okay. So your doubt, I
is
now get your
that
doubt.
vector
Okay. Wait.
has that some kind of implicit sequence like we have in MEL
Okay.
values.
See, actually, it was simplified for you people. what people actually do in practice is take the features as such from the wave to vec. No, what is that, averaging in the initial parts. Okay, so the actual procedure is you take a wave to vec, you get the features, which is like all the time frames you get from it, and then they feed it to eKappa TDNN to train the model. Okay, and then they perform. You can perform language identification. So it was simplified for you people. So we said, okay, because it is just a 3-language task, that's why your accuracies are low also. Okay. Because
Okay,
we
got
cannot
it.
give you big data sets. So to train an eKappa TDNN, you need lots of data. If we give you a lot of data, then for you to train the model, it's going to take a lot of time. That's why we simplified the task, making it a simple, vector, and then so that you can do something with lesser number of parameters and see what happens and get to know the implementation details. I'll tell
Okay,
you, if
maybe
I have to,
now,
if I have to
no,
train a Voxlingua model, which is actually a language identification data set, and if I have to train that model, it's going to take me a week at least with powerful GPUs.
I see.
Yeah.
So probably now, I think you may have to give a little more intuition into what eKappa TDNN is doing to bring in some that kind of order. Probably.
Correct. So what I will do now is I'll just show you the toolkit. Okay, how they have implemented eKappa TDNN in SpeechBrain. SpeechBrain is the toolkit in which this architecture, I mean, all the training setup is like usually kept. So I'll present entire screen share. Okay. So if you go to GitHub and just search for SpeechBrain, you will get this toolkit. So when you get into it, you will see something called recipes. Okay. So if you get into the recipe, I'm going to just give you a general overview of SpeechBrain, and then we'll get into how the eKappa TDNN is implemented and stuff. Okay. So if you get into SpeechBrain, someone is asking something.
I said, please go ahead.
Yeah. So we have something called recipes. So let me get into the recipes. Recipes is where all the example code is like residing. Okay. So this is like iShell data. I don't know for what test this data has been used. Common voice must be for ASR, and then GigaSpeech. This is another data set which is for ASR. Okay. IMOCAP is like, I think, emotion recognition. So you can see also LibriSpeech. For LibriSpeech, obviously it will be ASR. So we'll straight go to Voxlab because we have used the eKappa TDNN model, a pre-trained eKappa TDNN model, and it was actually trained with Voxlab data. So I'm going to go to Voxlab. If I get into Voxlab, I'll see something called speaker rec. So it's basically speaker recognition. And you will see this train speaker embeddings.py. So this is the training code, and you have something called hparams. This is nothing but all your parameters, how you pass your parameters. So train eKappa TDNN and YAML. So these are called YAML files. It's the format in which your SpeechBrain will accept all your hyperparameters. Okay. So you can see, your experiment folder, and then you have to give something called, so there is a data set called RIRS data set. It is like room, impulses, and noises kind of data set. What it does is, when you train your speaker embedding model, when you are passing your audio clip, okay, for the training, you also try to add some noise to the audio clips to make the model more robust. So RIRS data set and noise data set are basically for that. To add, it's actually having that it's basically a data set of noises and room impulses. Room impulses are required because a person can sit in different type of rooms, and then it's basically like some echoes and stuff coming back and adding to it, right? So you need the they calculate the impulse response of the rooms and try to use that in the audios to make the model more robust to wherever it's basically like wherever the speaker is sitting, the type of the room should not affect your embedding. So it's like that. Okay. Then you have a data folder. That's where your data will reside. If it is Voxlab data, if you have downloaded it from somewhere, you give the path to that data here, and it will actually this will SpeechBrain will automatically prepare your voxel data. When you get your data, it's not going to be in a format that SpeechBrain is going to accept it while training, right? So there is a prepare voxel.py code which actually takes that raw voxel data and prepares it in a format that SpeechBrain can actually use it for training. So you have trained data. I mean, this is how it will create train CSV, dev CSV, and some noise and ref CSV. And it also downloads the verification file, but we are not worried about speaker verification here, so I'm not going to talk about verification. So you all always know, always remember that in any verification process, classification is the first process. That's why we are going to go to this voxel speaker verification code, because the first process is what we are more interested in, the classification process. And then CKPT is nothing but in how many minutes gap you want to actually save your model. So you can say 15 minutes or 1 hour or 2 hours. So and number of epochs, batch size you mentioned, and this is like what's your learning rate. Base LR is so here they use something called a cyclic learning rate scheduler. What does a cyclic learning rate scheduler do? It starts from a very low learning rate, it slowly increases to a high learning rate, and again reduces back to a lower learning rate. So it keeps goes up, down, up, down, up, down in a cycle. So that's where your base LR and the LR are coming into picture. Step sizes, in how many steps you want to like reach this high, I mean from low to high, how many steps do you need to reach? So that you also define. Okay. Sample rate is about your audio file. So this SpeechBrain can accept your data if it is only in 16K sampled data. And you can define how your audio clips, it can be like 3 seconds, 5 seconds, but mostly the default is 3 seconds. And then you say how many MEL filters, MEL filter pack features you want. 80 you are saying. This deltas we are not using. Deltas are basically like derivatives of the previous frame with the current and something like that, but we don't use it. Out endurance is the number of speakers. We know before, if it is voxel 1 data plus 2 data, then it is 7,205 speakers. I'll show you. This is voxel data. Here you can see it's as 7,000 speakers, 2,000 hours, and all the gender distribution, utterance lengths, nationality, and stuff. So you have 2 versions of it. voxel 1 is a smaller version. It just has like very less number of celebrities. It's basically voices of celebrities during the interviews. Okay, they use that for building a speaker classification model. And voxel 2, you have more number of celebrities. So these two together are used. Where are we? Yeah, here. So the out neurons is like 7,200, and stuff. You talk about data loader, how what's your batch size workers, and then what kind of features you want to compute. We are interested in ML filter bank features, so FBank is here, and embedding model. Embedding model is something like we are using eCapa TDNN, but you are free to use any model, right? So you can define what model you want to use, because all these models are defined in the SpeechBrain Lobes models. So if you want to use a different model, like we have used transformer model in our transformers encoder in our research, so we can call that embedding model also. And for this eCapa TDNN model, you have to say the channels. Channels is something you have seen here. Where is this paper? The figure, yeah, here. These channels, right? So the how many channels do you want at every step? Okay, it's mentioned in this one. So the input channels is 1024, and then there are 3 layers. Each layer has 1024 channels, and then the final one is your after you have done your multi-layer feature aggregation, you come to 3072. Multi-layer feature aggregation is nothing but this part, this one, right? From all the 3 layers they have taken now, because it becomes 3 times the channel cross time. So here you will have to mention 3072. And then all the layers have different kernel sizes. They have different dilations. Dilations, I think you understand. It's basically like if dilation is 2, I'll leave out 1 frame in the middle, I mean in between, and then I'll take the other frame while I'm doing the convolution. Groups, yeah, we are not everything is like together. It's like we are not splitting and then doing grouped convolutions. So by default, it's like 1. Attention channels 128. I'll come to that when I'm explaining the code. Lin neurons, it's 192. This is our embedding dimension. Okay. So how many, what kind of embedding dimension you want, you can decide by varying this Lin neurons. And then you are using some classifier. It's basically defined in E-kappa TDNN, the classifier class. And we are saying the classifier will take an input of 192, which is actually our speaker embedding dimension. And then it is given to the output. Okay. And then you have all the other stuffs where you say, okay, how to add noise and all the definitions, how much SNR you want to give, and reverberation also, what you want to like put in there. Many things, all the augmentations, basically adding noise and then kind of masking some of the frames. All these stuffs are like defined here. Then you are talking about how to normalize your data. Then all the modules you're defined, what modules you want to like put in here. You're saying I have 4 modules here. Then the cost here. So cost is basically logs of max, but the loss function is additive angular margin. Nishant has explained. So the margin here we are keeping 0.2 radians and scale is 30. I'll come to that again while I'm discussing the code. So and then all the optimizers, LR annealing and stuff you are defining here. Okay. So now we will move on to the train code. Train speaker embeddings .py. Okay, going to the main. Yeah. So here you have some initial stuff. Let's not worry about it. So this is basically the preparation of voxel. We said, you get the raw or voxel data and then it is prepared in a format that is usable by the speech brain. And then once it is done, what you do is like you prepare the train data, valid data. You do the data IO prep. So let's go see what happens in the data IO prep. Yeah. In the data IO prep, what you do is after the train CSV and the valid CSV are generated by the prepare voxel step, you are trying to say that what is my 2 pipelines basically. Audio pipeline will take my, okay, so the CSV will have all these fields, okay. It's going to have all these fields because that's what it is going to operate on. So the audio pipeline is going to take wave, start, stop, and duration. So what does that mean? Wave is nothing but path to an audio file. Start is from which audio frame should I start and where should I stop. We know that it's going to be 3 seconds. So start and stop will be 3 seconds apart and duration is going to be 3 seconds. So what they do, they load the audio file, that segment of the audio file, they load it into signal, and sig is the signal and fs is the sampling rate, okay. And torch audio load always returns 2 information. So but we are interested only in signal. So this is all requirements of like all dimension compatibility that will always pop up in your deep learning. You will have to keep adjusting stuff accordingly. And then you return the signal. So with all this information, I have got my audio clip. I have loaded my audio clip. Okay. And then we go to the, it's called the text pipeline. What it does is again from the CSV file, there is something called speaker ID. Okay. So it will take the speaker ID and it will encode it. See, I cannot process speaker ID as 321 as such, right? So I have to give some numbers to it. So it will first, what it will do is it will take all the unique speaker IDs in the SPK_ID field and then it will encode it from 0 to, if there are 7,205 speakers, you will get from 0 to 7204. Okay. So that is your label encoder part. So that's basically your data prep. And then what you do is it's just creating some experiment directory and you are initializing a speaker brain class wherein you are saying what modules I'm going to use, what optimizer I'm using, and all the hyperparameters and other optional all this stuff. And then you are calling the speaker brain frit, which is actually going to call your the core train script of the speech brain. Okay, I'll stop till now. If there is any doubts, you can ask me, and then we'll move on to the E-kappa TDNN's architecture.
Yeah, one question. So do we not add all this noise and all in the first task for the language identification? Is it not required?
It is required. It is required. It is required and it will be added.
Okay.
Okay, yeah. So we will start the e-kappa TDNN architecture now. Okay. So that basically resides in speech brain. Again, go into speech brain. Then you will see something called lobes, models, and here we have e-kappa TDNN. You see here, this is our e-kappa TDNN. So what I'll do is, I'll first, here is the e-kappa TDNN class. So it is always a subclass of the NN module because we are going to build all the trainable layers, and so it is getting all the necessary information like how much should be your, what should be your embedding dimension, what kind of activation, and what channels you are going to use. These are all default settings, but whatever you have passed from your hyperparams are going to be taken here. Okay, and REST to net scale, stuff like that. So we'll start with, so the first thing that it does is it is going to build the e-kappa TDNN model, right? So what is the first block in your e-kappa TDNN model? It's a simple TDNN of kernel size 5 and dilation 1, a conv1d and a ReLU. Okay, so TDNN is always conv1d. It's a fashionable name, kind of just to grab some attention, they made a new term for conv1ds. Okay, and so the first block is defined here, which is taking input size, which is going to be your 80, and channels of 0, I think we saw 1024, kernel was 5 and dilation 1, groups are always 1, activation ReLU. So your first block is now a TDNN block of, right? So let's see what is a TDNN block now. It's defined in the start of this code. Yeah, class TDNN block. You see this here? A TDNN block is nothing but a convolution, which is nothing but a conv1d here. Okay, a convolution which is followed by an activation followed by a batch norm. This is your TDNN layer. We are using batch norms here because we are more interested in, you know, differentiating the speakers. So amongst the examples we want to like differentiate, so batch norms are better. And where we, yeah, so let's now move into the other blocks. So after the first TDNN block, what you see here is 3 squeeze and excite rest 2 block. Okay, so these are the 3 blocks, right? So it's trying to get those blocks. If you see here, length of channels will be like totally 5. So 1 2 3 length of so 3 blocks it is going to append. SE rest to net block, and it's going to say, you know, what will be the input channels, output channels, rest to net scale, squeeze and excite channels, and stuff like this. So we'll get into the details of what's happening in the SE rest to net block. SE rest to net block, yeah, going here. You see here, I'll open the so this is a SE rest to net block. You can see the first one is your conv1d, okay, simple conv1d. Your second layer is your rest to dilated conv1d plus ReLU plus batch norm. And then again you have a simple conv1d, then your squeeze and excite block. Okay, so if you see this, your first one is a simple TDNN. Mid you have a rest to net block, and then you have another TDNN, and then you have a SE block. Okay, so what happens now? The first step is the TDNN, next goes to the rest to net block, next to the TDNN, next to the SE block. So we have to see what happens in the rest to net block. So what are the parameters that are getting passed? Out channels, again out channels, rest to net scale, kernel size, and dilation. I think out channels will be some 1024. So let's go to the rest to net block. Rest to net scale is default 8 here. Where is it defined? Yeah. So if you go here, so it is again a TDNN block. Okay, your SE rest to net block is again a TDNN block, but the idea is what you do is, if you have something called, okay, let's say you have some C cross T input, okay. What it tries to do is, it will, so this C cross T, it will try to split into C by 8, C by 8, C by 8, okay. So 8 sets you will get, okay. So it is going to process them separately and keep adding them one by one. I'll show you what happens, but it's not in detail in this. 1 minute. Rest2 block. I kind of closed that window, I guess. Rest2 net block.
Similar to attention heads, huh?
It is similar to attention heads. The split is similar to attention heads, but the way it aggregates the features, it's different. Okay. I just need a figure to show you. I did that. This figure. Yes. So it's splitting. Let's say these are the 4 heads. Okay. But in the model, it is 8. Okay. So here the figure shows for 4. So it has 4 heads. So it split the input, that is X, into 4 parts. So the first part is unchanged. The second part passes through some conv layer, which is decided by whatever. I think it's also 3x1. And the third part, before it is passed to a conv layer, it will be the output of the second one will be added to it, and it's like some kind of aggregation. So what happens here? The context is, say, 3, because now this detail is added to this part. This convolution layer will have a broader context, and this will have a much broader context. Okay, so then you concatenate all the outputs from them and then send it for further processing. So it's basically to increase the global context of the model. And you can see here also, this is basically doing it. Okay, you can see self.blocks. It is getting the previous output and adding it to the current input, and your blocks is nothing but your TDNN block, which is again conv1ds. Okay, so that's your Rest2 net. Actually, we were near what? Pulling, where are we? So from squeeze and excite Rest2 net block, we went to the Rest2 net block, right? So we had one TDNN, one Rest2 net block, another TDNN block, and next comes the squeeze and excite block. So the information that it requires is the number of output channels, like what should be the output channels, and SE channels is basically this squeeze and excite operation. It goes to a lower dimension, performs something or some operation in that dimension, and again comes back to the original dimension. So I'll go to the paper now to show you what's happening. Squeeze and excite. Where we squeeze and excite block. Yeah, here we are. So what it does, say you have T time frames, it will take an average of the T time frames, and with that Z, what it tries to do is, you have this W1, right? So this is of the dimension R cross C. So R cross C into C cross T will give you R cross T. So after W1Z, you are in a lower dimension. Okay. And in that lower dimension, you have just do some, add all these biases and then have some nonlinearity. And then you try to bring it back to the original C channels, okay, the dimension C with the help of W2. Okay. And you have a sigmoid. So basically that R is nothing but your SE channel, the squeeze and excite channels. So you're going to a lower dimension and again coming back to a higher dimension, and you get something called a S out of it. So S is now a vector which is of dimension what? C cross 1. Okay. Now if I multiply it with an or with a tensor which is of C cross time, what I will get? I'll just scale the different channels, right? So different channels will get different weights. So it's basically trying to it enable the model. Okay, it's enabling the model to kind of pick which channel should I give more importance to. Okay, so that is the need of this squeeze and excite. And what they claim is based on, because it's averaging the frames, right? It's saying that they are trying to bring in the global context into the picture because of the squeeze and excite blocks. So you can see here there is an SE block. Where is this SE block? Class SE block. Yeah. So the implementation will be here. So here you can see con1, right? Even your feed forwards can be implemented with the help of con1ds. Okay. So that's why you are seeing a con1d here, though it is a matrix there. So with a con ReLU, another convolution layer, the first convolution layer has input channels and its output channels are the SE channels, which is the lower dimensional. So it's going to the lower dimension, and the next one is like from a lower dimension, it's coming back to a higher dimension. And then it's trying to, if the lengths. So initially I had said that, this model takes 3-second chunks to process the data, right? So during training, it is 3-second chunks, but during testing, it can vary. To handle different lengths, they prepare something called a mask, and then try to use the ones, because you will process in batches, right? Different audio clips can be of different lengths, so you pass something called a mask to make sure that you are using the information only in a particular, in which the audio is actually present and not the one in the padded area. That's why these masks are necessary. Okay, so SE block is also done now. And so you had 3 AC blocks, and then there is something called a and all these 3 are now going to be getting they are aggregated, right? So that's called a multi-layer feature aggregation. So let's go back to the eCOPA TDNN class. So we finished this layers, right? So the last layer would be your MFA. It's called the multi-layer feature aggregation. So what it does, it's also again a con1d. So it takes all the 3 layers output, and then it brings it to 3072, and then with all the kernel sizes will be like 1 only here. Dilation will also be 1, and you will have, after you have aggregated the features, if you see in the forward, so you had different layers, the data passed through the different layers, then you concatenated all the data and fed it to the MFA block. Concatenated the data from the 3 layers, right? Information from the 3 layers, and passed it to an MFA block. And then what you do is you call the attentive statistical pooling. So basically this is used to try to avoid the regions in the audio clip which are mostly silences. Previously, historically, people will always run a VAD before they train a speaker classification model. But with the advent of this attentive statistics pooling, we are not bothered about running a VAD before we pass. VAD is basically a voice activity detector, where you just find out the frames in which a person is speaking and the frames in which he is not, and you will remove the frames in which he or she is not speaking. But when you're using attentive statistics pooling, it's not a problem, because the model can itself understand in which frames the voice is actually present and in which frames the voice is not actually present. So we don't do a VAD, and this is taking care of that part. Okay. So this is your attentive statistics pooling. Let's see what's happening in your attentive statistics pooling. Attentive stats. Yeah. Attentive stats. Okay, so before that, again, let's go back to the paper. Attentive statistics pooling. Where are we? Yeah. Yeah. So here you see you have HT. Say this is just the last layers. Last layer. After you have aggregated all the features. At time step t, let HT be the value. What it does is it's processed by this weight matrix, which is R cross C. Again, R is a reduced dimension. You would have passed something called an attention channel. that is 128 for this eCuppa model. You are free to choose whatever you want based on your parameter budget. So you are going to some reduced dimension with this. So HD is transformed to 128 dimensions. And then what you do is, for every channel, so you have 3072 with you, okay, because you have aggregated the features from all the three layers. Each channel, each layer was 1024, so it is 3072. And this VC vector, right, it's going to be unique for every channel. So if there are 3072 channels, you will have 3072 VC vectors, okay. And these vectors, you are going to do dot product with whatever processed thing that came out, right. So you will do a dot product and you will get some scores from this, which is ETC. And for every time frame you will get it, okay, every time frame you will get it. So you will have to take a softmax across the time frames. Finally, you would have got for a particular channel how much importance should I give for a particular time frame. This information is held in this alpha TC, okay. So you are going to have how many alphas now with you? You will have whatever is your output size, you will have those many alphas with you, but the alphas across time will add to 1. So this alpha TC is now multiplied with your H, and then you take the average value, which is mu C, and then you take the standard deviation, which is sigma C. So these two information are obtained from the 3072. So you will have 3072 mu C and means, and 3072 standard deviations with you, okay. So here if you see, 1 minute, here. So it is always global context. So global context, what it does is, whatever X is there, it will again take mean and standard deviation of it, and then process it with the TDNN block, and then do the attentive stats pooling on top of it, okay. So then you have this con2D, which is actually con1D, which is defined here. Forward if you go, so here you have this. This is how you will get your attention values. You do a TDNN at tan H, which is your nonlinearity, and then your con. And then finally, you after you have the alpha attentions, you multiply with your X with that attentions and get your mean and standard deviation and get your pooled stats. So this is your stats. This is your vector from the model. After that, okay, yeah, then you have a linear transformation. This FC is what is going to bring down that big vector to 192 dimension vector, and then you will get a X value, which is actually your speaker embedding, and then you pass it to the classifier. Classifier is simply like you define, it's basically going to be a linear layer, and then what they do is, for your loss calculation, the weights will also be normalized and your X input will also be normalized, because we are more worried about the angles between the class vectors, which are basically defined by your weights and your input vector. So that's why it's normalized, and it is a requirement for the additive angular margin loss, okay. So this is now obtained, then you have to feed it to a loss function, right? So for that, I think it's here in SpeechBrain, nnet in losses.py. I'll finish it in 2 minutes, will not drag it further. Additive angular margin, yeah. See this here. So it's basically defined here. This is the loss function. Actual definition. I'll show you. This is basically your loss function. This is your loss function. So what it tries to do is, see, theta yi is actually the angle between the class vector and your embedding. Okay, and you are trying to add a margin to it. So this is basically your hyperparameter. We usually set it to 0.2 or 0.3 radians. So when you add a margin to it, what usually happens if so we have to reduce the loss, right? If I add m to it, what happens? Does the loss reduce or increase? Can someone answer? Are you people there or did I lose you? Is everyone here? Yeah, okay. So basically, if I add a m here, okay, it actually, the loss will increase. So to counteract, what will happen is this theta yi should reduce. So this theta yi, when it reduces, it means that the embeddings are becoming more compact, like this. Yeah, like this. So without that margin, let's say it was distributed like this. With this margin, it is trying to force your embeddings to be closer in order to reduce the loss. That's why these are like now embeddings, okay? Or these are all like embeddings. Let's say this is for one of these speakers, if these are the embeddings. For another speaker, these are the embeddings, and there is some margin between them. So that's the motto of using the additive angular margin loss, and it's basically implemented here. All the math is, if cos theta plus m, they have just expanded it, and then if it is a target, then you have to use theta plus m. If it is a non-target, you should not be using theta plus m, as shown here. Yeah. So for whatever we are interested in, only for that class we have to put in a m. For other classes, we just leave it as such. Okay. So that's what is being taken care of here, and it is multiplied by some scale in order to make it bit stable, and you will just pass it to the log softmax. That's it. So this is how your whole model is like implemented, and we cannot like, my one model is just running. I can show you what's happening there. Wait a minute, screen. This is like a model that is already in the training process. This is very small data. What I am trying to do is actually fine tuning of a bigger, a model which was trained on bigger data. So when you just try to do this, CUDA visible devices is like when you have a server, and if you have so many cards, we just define which card you want to put your model into, and then this train speaker embeddings I'm calling. This original is for my reference. It's actually a copy of the actual train speaker embeddings.py, and then you give the parameters file, okay, the hyperparams. It's in the hparams folder. This if I am just passing it, and then it will start training if all the data and stuff are in place. It also says how many parameters are in the model, and because this is fine tuning, it is loading a checkpoint and stuff. Otherwise, it will not say anything. Okay. Any doubts? Any clarities or questions?
That was very elaborative. Thank you very much. Can you just give some metrics on how much time did you need to train some
Voxelab.
typical
Voxelab,
data?
we usually train it for 9 epochs, and each epoch is like 17 hours.
Oh, okay.
Yeah.
On that one GPU, is it?
Yeah, on one GPU card, yes. Actually, speech-based models, no, to train it, it will take a lot of time, because what we are talking is like samples. If it is 3 seconds, if it is 16 kilohertz data, then every second you have 16,000 data points, and with that you will compute your filter bank features. So every 10 millisecond you get one frame. So every second you will have how many frames then? 100. Am I right? I remember that it is 100 frames. So total 300 frames will come. But to get to that frames itself, some computation is happening now in the background. So it takes a lot of time.
Okay.
It's not as easy as a image task or even a text task is easy, I would say, compared to speech.
Right. Get it. Thank you.
Yeah. Any other questions? What you can do is take a small data set. You can try fine tuning and all. I think it should not take so much time. You can take the trained eCuppa model, download it from wherever you can. I think even in SpeechBrain you will have a trained eCuppa model, I guess. So download it and then you can try to install the SpeechBrain and get a small data set that you can even a subset of Voxelab if you can get, or you can record your friends' voices if you want, but that won't be sufficient. That's the problem. Maybe Voxelab 1 you can try, that might be a bit faster if you want to do some kind of fine tuning and see. Okay, that can help you understand how to use this toolkit and what components are residing where and all. I mean, it will take some time to understand, but once you start using it, you will get used to, we have been editing these codes. These are what I taught you was a default setting, but we have been editing these to make architectural changes, uh, for the purpose of research and stuff. Anything
got it.
else?
Thank you.
Okay, fine. So should we stop now? Mr. Nitin, are you there?
Yes, Matil. I think
And
we can stop it now. Yes.
we can stop, right? So I'll then leave the call. Is that okay?
Yeah, that's fine. Close the call.